Good day, students, and welcome to today's class in School of Chemistry. We'll be looking at the concept of transition elements. Transition element. We'll be looking at the concept of the periodic table. And the transition elements are part of the periodic table, and they are a group of elements that exist between group 2 and group 3. In between them, this is where the transition elements are found. They are found there. And according to IUPAC, transition elements simply are elements that have incomplete or partially filled d orbitals. Incompletely filled or partially filled d orbitals. So if you have a d orbital that is partially filled, that is what makes you a transition element. I have such elements in the periodic table from group 3 to group 12 in the periodic table. This is where you find them. Now when you draw your periodic table, you have your group 1 here, group 2. Then between group 2 and 3, like this. So between here, this is the structure of the periodic table. Between here and here, between here and here is what we're talking about. All the elements here all have incompletely or partially filled d orbital, and that's what makes them what? Transition elements. Now, we also have here the F block elements, which are part of the transition elements, and they are referred to as the inner transition element because they have their valence electrons in the F orbital, while the transition elements have their valence electron in the d orbital. The lanthanides, call them the lanthanides, and the actinides, which make up the inner transition elements. They are inner transition elements because their valence share exists in the F block of the periodic table, in the F orbital. I will call them, they make up the F block of the what? Periodic table. So while the metals make up the S block, the non-metals make up the P block, the transition elements makes up what? The D block, while the lanthanides and the actinides makes up what? The F block. Now, the transition metals, all of them follows a particular configuration, which is N minus 1, N minus 1, D, D1 to 10, NS1 to 2. This is the general formula in the electronic configuration, where N denotes the energy level. So you have an N minus 1 D, which represents that you can have electrons from 1 to 10 in the D orbital, and an S orbital with electrons from 1 to 2. Now, some elements like zinc, scandium, are not classified as transition metals because they do not follow this rule. The d orbitals of zinc in particular is not what? Partially filled. It's not partially filled. It is completely filled. The atomic number for zinc, is 30. Am I correct? I think it's 32 or thereabout. Okay, I'll find out. Atomic number for zinc. The atomic number for zinc is 30. I'm correct. Zinc is 30. And you do the configuration for zinc. Zinc is 30. So I'm going to have an argon core, 3d10, 4s2. Now looking at the d orbital of the zinc, the D is not partially filled, and that is why it's not treated as a transition metal, but it is in that block of the periodic table because it is what? The D block. Also, the same thing happens to what? Scandium. Now, let's look at the electronic configuration of some of these, the first two rows of the transition elements. Like we were saying, we say the electronic configuration of zinc, mercury, and cadmium shows that they do not have partially filled d orbitals. Now let's look at these elements on the board. They are all transition elements. We're going to look at the electronic configuration. These are all transition elements. Number one is scandium. I was giving scandium as an example. Rather, it is cadmium that is not a transition metal. This is a transition metal. Cadmium is not a transition metal. All right. Cadmium is 21, and we're going to have. Before that, let's look at the configuration for argon. Argon is 18. So we're going to have 1 S2, 2 S2, 2 P6, 3 S2, 3 P6. You have not been in our class. If you are just joining, please go through our former lectures. We have done electronic configuration. So if you can have 4, 10, 18. So now, because it's a noble gas, whenever we write this, it means it's an argon core and it represents the whole of this configuration. Another noble gas is krypton. Krypton is 36. We're going to have 1 S2, 2 S2, 2 P6, 3 S2, 3 P6, 3 D10, 4 S2, and 4 P6. Let's count. 2, 4, 10, 12, 18, 28, 30, 36. And you can refer to this as the krypton core. And we'll be using it in our configuration. Anytime you see this, it is an argon core representing the whole of this configuration. You see this is the krypton core and it represents the whole of that configuration. So let's come here. Scandium is 21. The electronic configuration is going to be 3, excuse me. It's going to be the argon core, that's the whole of that configuration, 3D1, 4 S2, 21. This is 18 plus 1, 19 plus 2, 21. Now look at the partially filled d orbital that makes it a transition metal. Number 2, 20 Ti, which is 22, is going to be the argon core, 3 D2, 4 S2, followed by V, which is 23. We have the argon core, 3 D3, 4 S2. Then chromium, which is 24, going to be the argon core. Now look at this. We have the argon core, 3 D5, 4 S1. Now why 3 D5, 4 X1? It is because a halfly filled orbital gives a sense of stability to the atom. You know that the d orbital has 5 sub orbitals. 1, 2, 3, 4. 1, 2, 3, 4, 5. These are 5. So since we have 5 here, we're going to have 1, 2, 3, 4, 5. While the S level has only 1 suborbital. So if each of the orbitals is halfly filled, it has been accepted that halfly filled orbitals give a sense of stability. So all of them being halfly filled will make the atom more stable. This is why the configuration goes like this. Now our manganese 25. Manganese 25 will go with the argon core, 3D5, 4 S2. We have iron, we'll go with the argon core, 3d6, 4s2. Then cobalt, 27, going to be the argon core, 3d7, 4s2. Then we'll have nickel, 28, going to be the argon core, 3d8, 4s2. Am I correct? Yes. 3d8, 4s2. Then we have copper. Copper is 29. We have 3d9, 4s2. Zinc is 30. We're going to have the argon core, 3d10, 4s2. Now look at the d orbital. For all these elements, the d orbital is supposed to have a maximum of 10 electrons. So we can say from here up, all of them are partially filled. Only zinc is completely filled. The d orbital is completely filled, and that's why it is not treated as a transition metal, because the d orbital is not completely filled. Let's look at element Y, 39. Now 39, we're going to have the krypton core, which is 36. The krypton core already has atomic number 36. Followed by what? After the krypton core, we're going to have 4d1, 5s2. Then Zr, atomic number 40. We're going to follow the krypton core, 4d2, 5s2. Let's look at for the other element, cadmium, which we say is not the transition metal. Let's look at the configuration. It is 48. So it's going to follow the krypton core, Kr, 4d10, 5s2. Can you see that? So the d orbital in the krypton core is not complete, is completely filled. So it cannot be a transition element. So going by our definition, we say that the IUPAC definition, we say that transition elements are elements with partially filled d orbitals. Partially filled d orbitals. So elements like cadmium, which has a completely filled d orbital, and zinc with a completely filled d orbital cannot be classified as what? Cannot be classified as transition element. Now you can be hearing the word transition element or transition metal. They are used interchangeably. Is that okay? All right. Please, if this is your first time of joining this channel, do not forget to subscribe to the channel if you're on YouTube. Also, if you're on Facebook, do not forget to follow us. Share, subscribe, and like. And also, leave your question in the comment section. Leave your question in the comment section. I will equally attend to them as we progress. We'll be doing a whole lot in this channel together. Now, let's look at the general properties of transition metals. I'll be looking at just few. Just three of them. There are a whole lot of properties, just three that are very basic. One, they form colored compounds and ions. Transition compounds form what? Colored compounds and ions. Why do they form colored compounds and ions? They do form colored compounds and ions because of what? They are incomplete or they are partially filled d orbital. The electrons in those orbitals can transit from one of the sub-level in the d orbital to the other. So in the course of changing, it gives rise to what? Color change. We'll be discussing that as a topic in this particular class that we're in. We'll discuss color change in the transition metal as a topic. But what gives rise to that colored ions is what we call the DD transition. The DD transition, that d orbital transition of what? Electrons. Now, second, they exhibit variable oxidation state due to low gap in energy level between possible oxidation states of these elements. The energy gap here between dx, dz, ds squared, and all that is very, very, very small, so it can change. 3, they are paramagnetic. Paramagnetic because of the presence of unpaired electrons in what? The d orbital. These unpaired electrons in this, almost all these d orbitals have electrons that are unpaired, and that's what makes them what? Paramagnetic. It's the presence of unpaired electrons that make a substance what? Paramagnetic. Please, if you have any question on this, leave it in the comment section. I'm eagerly waiting for you to answer. If you have not subscribed, do not forget to what? Subscribe. Thank you.